是我们华人还是稍微谨慎一点。
Extra protein, TTCG, small people.
Hello, everyone. Welcome back. All right, so today we're going to continue on our recommendation systems. Okay, so far, what have we talked about? We have a content-based system. We have collaborative filtering. And we say collaborative filtering, you have user base and you have item based, right? So user based is you just compare all the users, you find similar users, and you use similar users to make the recommendation. Item based, you compare all the items and you use similar items to make a recommendation. So just a brief recap. If this is your active user, you want to make a recommendation to this active user. So you have a product, you do not know how would this active user rate this product, right? So you look at your database, and in your database, you have many users. You find the top K similar users, top K, user 1, user 2, and so on. And you use their similarity and also their rating to this specific product to generate a weighted average. So you get this number, right? So let's say you have K equal to 1. That means you just find the most similar user. You just say whatever this user rated for this item, I will use that to predict, well, I will just use that as the rating for A. One example would be if you look at user A's rating and you say user A's average rating is 3. You look at this most similar user, and the most similar user's average rating is 4. And this most similar user rated this item 4. How would you predict the rating for the active user? Anybody? Anybody still with me? Okay, so user-based collaborative filtering, right? We are looking for the most similar users to your active user here. And let's say in this case, K equal to 1. So we just find the most similar user to A. So you get what? 1 user. Our goal is to be able to predict A's rating on this item based on this most similar user. And we know that A's average rating is 3. This most similar user's average rating is 4. In this case, this most similar user rated this item 4. Give this item a rating of 4. So how would you predict A would rate this item? Rating from 1 to 5. 3, great. Okay, thank you. I'm relieved. At least some of you will be able to answer this question. So it's 3, right? Because you want to look at normalized rating and you are using 1 user, so it's 3, not 4. Great. All right, so next, you have an active user and you want to predict for a certain product. Now you are going to use item-based collaborative filtering. So you look at all other items. This item user rated 4, and this item user rated 5. This item user rated 3, and so on. And let's say you want to find K most similar items to this item, and your most similar item is this one. So K equal to 1. How would you predict A's rating on this item? 5. Great. So why aren't we care about all this normalization anymore here? Well, because you are only working on 1 user, right? So all this rating are already normalized for this specific user. This is user A's rating. Excuse me. All right, so let's say you have K equal to 2. And let's say this one has a similarity of 50%. This one has similarity of 50%. This one has a similarity of 20%. What would be A's rating for this product? K equal to 2. Okay, so great, 4.5. So 4 times 0.5 plus 5 times 0.5 divided by 0.5 plus 0.5. Okay, all right, so that's it, very easy. And we say that item-based approach in practice would generate a better prediction, and also item-based approach is better in terms of scaling up in processing large numbers of users and items, because you can pre-process all these similarities between items beforehand. Okay, so that's the summary for your item-based and user-based collaborative filtering. Today we're going to talk about some extensions, and you want to pay attention to this because these are really, well, first, they're very interesting and they're also very practical. And in your in your final project, you will definitely need to use some of this to improve your result. So Christina has a question. The book isn't as detailed in collaborative filtering as we are covering in lecture. I think it's pretty detailed. I'm not sure which part you are talking about here, because the idea is very simple. Yeah, it's not very long. The idea is very simple. Okay, so let's look at this. I'm going to tell you some extensions to all this collaborative filtering method, and you will see why we need all these extensions. So some extensions has been studied to improve the performance of collaborative filtering approaches. This typically involve modifying the similarity weights, and we will see why we need to modify this. Or use some method to guess missing values, and we will see why this is important. Okay, so we just covered this too. Okay, mute it. All right, so extensions. In many collaborative filterings, pairwise similarity is computed only from the ratings in the intersection of the items both the users have rated, right? Because very often we are only looking at co-rated items to compare two users. This is not very reliable when there are too few votes. So let's say if two users only have one co-rated item, does that mean, and they're exactly the same rating, does it mean the two users are 100% similar? It's not, right? So if two users has too few votes, then we want to be able to penalize this. And also, the previous approach just we talked about focus on co-rated items and does not take into account the global rating behavior reflected in the user's entire rating histories, right? So you only look at the co-rated items, then you're going to miss many stuff. So what we can do to overcome these two challenges is to assume some default ratings for the missing values. This can actually improve the collaborative prediction performance. Let's look at here again. So if you look at here, user-based approach, when we are generating the weight, this weight is what? Similarity between two users, right? User U and user V. And if you look at how we calculate the similarity, this is Pearson correlation. This is for all the items that both user U and user V has rated, right? So you will have that problem if this I, the set of I has very few items, this will not be reliable. So there is a question from Vedant. In user-based method, when making a prediction, the definition of RA bar here and RU bar here says the average rating for user A and U on all other rated items. Does all other rated items means average? Yeah, it's usually except the items that being predicted. That's just for your Pearson, for the sake of your Pearson correlation, you want to be consistent, right? Because when you are calculating this for user A, you do not have the rating for item I, right? This is the number that you are predicting. So when you are calculating this, you don't have a way to use your rating for user A on item I. And if this average is excluding item I, that means we want this to exclude item I as well. But in practice, it doesn't really matter much because this number would usually taken from a large reviews. So user U could rate it for 200, 100 items, and only missing include one or excluding one does not change this much. Okay.
So it won't be just correlated items, right? I mean, it will. So when calculating the weights, it is just correlated items, but then when predicting the rating, the RU bar will have a different value than what it had when calculating weights. I mean, if you can go to the definition of the prediction formula, like it's on page 20. Okay, so
Average ratings for user A and user U on all other rated items.
yes, so it's not correlated, right? Like
No,
for
it's not just correlated.
it's
This is
not just everything,
right. This is
and
everything.
but for weights it's correlated, like that's different in weights. Like when you calculate WAU, for example.
Right. For WAU, you can only use correlated.
Oh, okay. Okay, thank you.
Sure. That has a reason, right? So you don't have to remember this. For this, you can only use correlated because you are looking at the same item. How do the two different users rate it on the same item? So you can only use correlated. But for this is generating a baseline for this user A, right? So you want to know how usually user A would vote. So this is taking all items that you can find. And for this, the reason why you want to exclude I is we cannot include I here. So you might as well exclude that. But the problem is then you have to change this value every time when you are comparing two users. So very often if this user use rated data is large, you generally reuse this average for every time when you are comparing this user U to other users. All right. Okay, so we talk about to overcome these two challenges, we can assume some default values so that we will not have that many missing ratings and we will be able to find more correlated items for a user pair. For example, some approaches for default voting. This first approach account for small intersection sets. Say if two users have very small number of correlated items, this approach will reduce the weight of users that have fewer than 50 items in common. So it's a scale that weighting number. It doesn't really imputate or do anything for the missing data. It just says if the correlated items between two users are too small, we'll just penalize this. The second approach will use an average number of a small group of correlated items as the default rate voting so that they can extend the user's rating history. Right, so let's say you have one user UA and another user UV, and their correlated items are only 20. You can take this 20 correlated item and you can take all these other items and trying to use this 20's value to imputate for the missing data. So eventually you might have 60 and 60 correlated items so that you will be able to do a better collaborative filter. But this highly depends on your application. So if you really want to do this, you have to read the paper and see how they apply this approach for their application. It might not work for every application. So by application, I mean sometimes you have movie recommendation. Other times you have book recommendations, or you have like Yelp restaurant recommendations. Every data set, every application would require a slightly different twist of the technology that you're going to use. The third approach uses a neutral or somewhat negative preference for the observed ratings, then compute the similarity, right? So this is a very simple imputation method. you just every time when you see a missing value, you'll probably just use the average rating for that particular user for that missing value. So eventually the correlated items between a pair of users will be large. Other approaches, here universally liked items are generally not as useful in capturing similarity as less common items, right? Because some items are liked by many people and you don't really want to use that to calculate your similarity weight. And we have a really good example before, that's the inverse frequency, right? Remember your TF-IDF. If a word is very popular, exists in many documents, you don't really want to use it to characterize the topic of a document. So you can calculate the inverse frequency by doing this. You have the total number of users. You have the number of users who have rated item J. This is the inverse frequency for item J. And you can see that if everyone has rated item J, this Fj becomes 0, right? So you have 1 and 1 log 1 is what? 0. Then you can take that inverse frequency and multiply it by the original rating. It will give you a new value. Then you just follow the original method to generate the prediction. So for very popular items, the rating RUI will be reduced. Less popular items will have great effect on prediction. Okay, so as how you would apply this is not very important, like here. The way they apply this is to generate a new rating and use that for a prediction. But the takeaway here is this is really cool, right? You know that universally liked items are not as useful, and you do have a way to capture universally liked items, right? Once you can capture it, you can try different ways to use this frequency, this inverse frequency, to help you do this. Okay, so that would depend on you how you take your small data set, test it, and then apply on large data set. So remember, everything I said here is to help you with your final project once you are able to build your assignment 3. All right, so next one, we can do transformation, apply to the weights. So why do we want to do transformation? Well, very often you have a few high weights and you have lots of low weights. For example, let me draw a chart. Let's say this is called similarity, and this is user. Okay, every bar is, this is a similarity to user A, active user. Every bar represents a user. So what does this chart tell you? This tells you that you have all these users that are very similar to user A, right? So their values are pretty high. But you have a long tail. You have many users that are not that similar. And this can be a challenge for your collaborative filtering method because you need to pick a K. For example, let's say your K is 150 users, then it might be something like this. But in practice, you don't want to have this many users. Well, you want to have 150 users, but you don't want this part because this is just noise. Their similarity to your user is too little and you don't want to use them for prediction. So how do you still keep these 150 users at the same time, amplify this and remove the noise? So that's the solution here. It's actually very simple. This is your new weight. You take your old weight. This is your old weight, and you do a power to the p minus 1. Okay, not p. So this is the case amplification power. If it is larger than 1 or equal to 1, you will be able to see this becomes, if it is 1, this becomes what? 0, this becomes 1. So the new value is the same as the old value. If you have 2.5, this becomes 1.5. So this becomes what? W's 2. Right. So if you look at some example here, when your weight has a large value, because your weight is the largest number would be 1, and it will remain high because 0.9 to the power of 2.5 is 0.8. For your W, when it's 0.1, right, the noise here, the weight becomes small. 0.1 times to the power of 2.5 is 0.003. So it does not have high impact on your final prediction. This is a very, very useful technique that you would want to use in both your assignment 3 and your final project. Another one, when your rating data for CF tasks are very sparse, it's difficult to produce accurate predictions using Pearson correlation-based CF because you are only looking at correlated items. Like the other extensions we talked before, people start to use imputation-boosted collaborative filtering. For example, you will use some imputation technique to fill in the missing data. One simple way is just to use the average rating for that user to imputate the missing data. Or you can have some other way, might be able to group the items together, see they're similar items, and you use the average rating of similar items to imputate the missing data. But this, of course, depends on if you will be able to find similar groups of items. Then use traditional Pearson correlation-based method and do the prediction. So example imputation technique, mean imputation, very easy. You just take a mean number, mean rating of all the items. You can do a linear regression, take a few items, trying to predict the missing value, predictive mean matching. Again, take the mean, but generate a machine learning method, predict for the new mean if you add new data set. Some Bayesian method, if you have some prior, how would you be able to predict for the mean and all that? So lots of method that you can do imputation. When you are selecting the method that you want to use, 2 criteria. First, computational time, because you're often looking at millions of users and millions of items. So some of this approach might not really work. Second, depends on your application. Some items, you might already have some content-based features that you can use to group them together, right? If you can do that, then you will be able to say, all right, let's find a cluster of items, use the mean value for prediction. But if you don't, you probably can just use the mean or other machine learning method to help you, depends on the available features you have for the users and the items. So this is open-ended. All right, so this is everything I want to say about the collaborative filtering methods for a recommendation system. Any questions before we move on to the next topic? Okay, the next topic is going to be pretty short. Let me find the slides. And I'm going to put the slides on Piazza. Okay, so you should be able to see the slides on Piazza. Okay, so the third part of our collaborative filtering techniques, we talk about CF-based method, right? And this is built in the model using the user's past behavior, similar decisions made by the other users, and then use the model to predict. So two methods we talk about are user-based and item-based. So today we're going to quickly go over the model-based approaches. And this, you can actually find a function in the Spark ML lib. So model-based collaborative filtering. So in the model-based collaborative filtering, we want to be able to provide recommendations by estimating some parameters of statistical models for user ratings. This is very vague, but you're going to see some examples. Design and development of the models can allow your system to learn and recognize complex patterns, and it's usually based on some training data set, so this is supervised learning. Then once you are able to build this model, you will be able to take that model based on the parameters and make the predictions, so intelligent predictions. Many methods can be used, and we're going to cover a few of them today. So clustering-based CF is the first one. So clustering-based algorithm, a cluster is a collection of data objects or data points, so that in a cluster, data points are similar to each other. If the two data points are not in the same cluster, they are dissimilar. We need to be able to define a similarity measurement, right? Because we talk about similar, dissimilar. What do you mean by similar? And some measurement that we can use Pearson correlation, we can use cosine similarity, we can use Minkowski distance. So if you are not familiar with the Minkowski distance, it's just a general form of your Euclidean distance. If you have 2 here, if you have 1, this will be Manhattan distance. So as in the slides, we saw that we always use Pearson correlation. But at the beginning, we talk about cosine similarity. It's always important to study your data to know which similarity measurement would be useful. So here's something that you should read. And in this blog post, they talk about how they take a small data set and test both Pearson correlation and cosine similarity, and eventually they figure out cosine similarity is actually better for their data set to build a recommendation system instead of using Pearson correlation. So, all right, let's say you can pick a similarity measurement. Then we can start to look at clustering algorithms to cluster your data. So common clustering methods, k-means and hierarchical clustering are probably the two most commonly used clustering method, and we're going to talk about them, I think, after 2 weeks. But in your Python package, your scikit-learn, you'll be able to see many different clustering algorithms. And based on your application and your data set, you will need to choose one that would work for you. So let me just briefly talk about this chart here. So each chart here is a 2-dimensional space. And each dot in a chart is a data point, right? So this is a data point in a 2-dimensional space. But in general, you can think of you have multiple dimensions, usually high dimensions. And every clustering algorithm has its own advantage and its disadvantages. And you can see how they treat clusters differently in each example, right? Like this one, look like they have cut your data point here. So you have a group, you have another group. But for this algorithm, you can see that connected component is important, or here, and until here. right? So two disconnected components are their own cluster. And you can also see the one like with circles and other dots. So lots of clustering methods, lots of different results, depends on your application and data sets you want to test it. There's no universally excellent clustering method. All right, so in the clustering CF algorithms, we actually just take your user data or item data and perform a clustering algorithm based on your defined similarity matrix. But this clustering is just an intermediate step. Once you have the clustering, you just take the clustering for further analysis to make the recommendation. For example, you can partition your user or item data into clusters. Then you can start to use your memory-based method with Pearson correlation to make predictions within the cluster. So the idea here is items or users within a cluster are more similar than items or users across clusters. So by focusing on one cluster, you should be able to generate a better result. And clustering algorithms usually have better scalability than typical CF methods because you only make predictions on small clusters rather than the entire customer base, either users or items. And all this complex and expensive clustering computation can run offline, right? So you do not need this in runtime, in real time when you are making a recommendation. But sometimes your recommendation quality can be low because, well, first, optimal clustering is impractical. Second, if you look at this description here, your first goal is to partition the data into clusters. Your second goal assumes that every data point in one cluster contain either similar users or similar points so that you can use them to make prediction, right? But your goal here is not always aligned with the goal here. Depends on your similarity matrix used in doing the clustering. All right, optimal clustering over a large data set is usually impractical. Most applications use greedy cluster generation techniques, and we're going to talk about some clustering techniques later, so not today. All right, so the second model-based method is regression-based method. So regression-based methods are really common to handle numerical ratings. And regression methods are good at making predictions for numerical values. You can use it as an approximation of the ratings to make predictions based on the regression model. For example, let me show you here. You can start by model your data using a linear predictor function. And this linear predictor function will have some unknown parameters. You can estimate them from your data points. This model is called a linear model. If the goal is for prediction, forecasting, and all these different tasks, you feed the predictive model to an observed data to get of y to get the x value, then you will be able to make the prediction. Let me show you here. So linear regression, I'm sure many of you have seen something like this before. Let's say you have your GPA and you have your salary, right, 2-dimension, and you have a trend line. You have many different algorithms to be able to help you find this line with different goals. Maybe you want to normalize the distance like this, minimize the distance from a point to the line, straight line distance, or a distance like this. Right, depends on your goal. But in general, you are going to find a line, a straight line that will be able to describe your data. So when we say model and its parameter, the model we're using here is y equal to ax plus b, right? This is x, this is y. And your a and b are the model parameters. And how do you find a and b? Well, you take all your blue points These are your observations, trying to find a straight line that will minimize the distance. Then you will be able to find A and B. So once you find A and B for X with an unknown Y, you'll be able to use this line to make the prediction, right? So in a recommendation system, if we can develop such model and we take some additional value of X, we will be able to predict for the Y. For example, let's say you're building a recommendation system. This is your utility metrics. This is your user. This is your item, right? You want to use collaborative filtering because you know it's pretty accurate. It's a pretty good method compared to content-based method. But the problem is your metrics is very sparse. So how do you predict? Remember, we talked about one of the extension is you can imputate some of the missing values first, then you use collaborative filtering, right? So the way to imputate is you can build a linear regression model. You can take some content-based attributes of all the items. So for example, you can say, I'm just making up this example. You can say this is price, this is rating. And for this user, the more expensive the item is, the user will rate it highly. And you'll be able to find a line. And based on this line, if you have a question mark here, you just look at this price because you know the price and you guess for a rating. So you say this is 3. For this one, this is here, you guess this for a 5. But you are not done yet because this is not accurate, right? This is a very simple heuristic. To be able to predict for the true high rated item, you will just then use a CF approach. But this time, the metrics is not sparse anymore, so you should be able to perform better than using your original metrics. All right, so there are also other matrix multiplication, matrix manipulation methods to do model-based CF, and we're not going to cover them today, but you can find them in your Spark machine learning library, and they will be very useful for your final project. You can also ask your TA as well. All right, so that's everything for model-based and neighborhood-based collaborative filtering approaches. Let's look at some challenges. For collaborative filtering method, one challenge is data sparsity. So many commercial recommendation systems are used with very large product sets. When you have very large product sets, that means most users do not rate most product, right? Then your user item metrics, your utility metrics is very sparse. Then it will be difficult to find sets of users that would have similar ratings. The approaches that you can use would be, well, you can do SVD. I think we're going to cover this in your clustering algorithm in your clustering week. So SVD is a method that you can take a large matrix, you can reduce the dimension of the matrix. Then you will be able to find representative users or items. Right, so using SVD, you will be able to remove the unrepresentative ones. Then you will be able to reduce the size of user item metrics. Latent semantic indexing is a technique to learn the similarity between users based on the representations of users in a reduced space. So this is also machine learning methods. So one example of latent semantic indexing is your Google search, right? So let's say if I search, depends. If I search Yao Yiqiang and without typing enter, you can start to see Google will start to recommend other keywords that you can use together with this keyword, right? So this is done by latent semantic indexing. This is telling you that these two words or these word pairs, phrase pairs, they have very high similarity in terms of if you take them together, they can represent a concept, right? So it's not as easy as frequently searched together terms. You can also do principal component analysis to reduce the dimension of your data set. This is very similar to SVD, but not quite the same. But very often when people do principal component analysis, they use SVD to solve the matrix computation. All right, so the takeaway here is data is sparse. You can use dimensional reduction technique to handle sparse large metrics and generate a condensed smaller metrics for your recommendation system. Dimension reduction techniques when users or items are discarded because you want to compact your metrics, sometimes useful information for recommendations could be lost. The quality of your recommendation may be degraded. Other challenges, we have co-star problem. When a user or item just enter the system, it's almost impossible to find similar items or users, right? Because you do not have enough information to make good recommendations. Remember, your content-based system do not have this problem for items, still have this problem for users. For new item problem, you cannot recommend it until some users rate it. Also apply to obscure items that nobody really buy, nobody really rated. This is called the first rater problem. For a new user, this new user do not give recommendation. We cannot give good recommendations because we do not have rating or purchasing history from this user. And this is also the problem of your content-based approach. So approaches, content-based systems do not apply on ratings from other users, so you will be able to handle new item problem. Then today we're going to talk about hybrid approaches. You can use external information to produce predictions for new users or new items. And research on effectively select items to be rated by a user to improve the recommendation performance is still ongoing. Remember that Amazon Vine program I was talking about? This is similar to that, right? You have limited amount of resources that you can spend to ask people to to enter reviews so that you have a dense matrix, but which item or which user you want to ask to do this. All right, so let's take a 10 minutes break, come back at 7. If you have any questions, please put it in the chat. I will answer them when I come back. Hello, I'm back. All right. Okay, so continue. I think we talk about this co-star problem. All right, synonyms. So we are still at the challenge. There's a lot of challenges in building the recommendation system. In your homework assignment, you will be able to see it's really difficult to build a recommendation system. So it's really cool you start to build one. So synonyms. Sometimes you have the same or very similar items that can have different names or entries. This is especially true when you look at eBay, right? The user can provide names of an item, descriptions of an item, which make it difficult to know they're the same item. Most recommendation systems are unable to discover this latent association. They do not know two items are actually the same items, although they might have different names. So that they will treat these items differently, then you will decrease the performance of a CF systems, right? Even if they are combined into one item, it's already difficult to find correlated items or correlated users. Now you're splitting one item into several items. It's difficult to even find the correlated items or correlated systems. So approaches, we can do automatic term expansion or construct some thesaurus to be able to say, hey, these two items are the same items, but some added terms may have very different meanings than intended, so it's actually pretty tricky to do this. You can also use SVD technique, this latent semantic indexing, like we said before, find some semantic space to describe items. Then in that space, terms and documents, when they're close to each other, they might represent the same concept, like in the Google query example, right? So if you Google Yao Yi Chang, it recommend data mining. So that's probably these two terms represent the data mining course at USC. Then you will be able to combine items and to make a recommendation. Scalability is an issue for CF-based method as well. Traditional CF systems suffer scalability problems at very large scale, right? When you have very large items or very large number of customers. When it's too large, linear algorithms is still not very good, right? Find similar users or find similar items become a problem. Dimension reduction could be useful because you will be able to reduce that utility matrix into a small one. But sometimes it's difficult to do because it's expensive to do dimension reduction. Memory-based CF algorithm would have good scalability, but this one you would use item-based method. So instead of calculating similarity between all pairs of items, you calculate similarity between correlated items by a user, right? So this will give you much better scalability. You might have other problems, gray sheep, black sheep. Gray sheep, users whose opinion do not consistently agree or disagree with any group of people. So this type of user do not benefit from collaborative filtering. Hybrid approaches would work if you combine CF approach with content-based approach. We're going to talk about hybrid approaches today. Then you base your prediction on weighted averages of your content-based prediction and your CF predictions. You might also have black sheep. That means this type of users, you cannot predict them. Their tastes are so different from all other people. You just consider them as an acceptable failure. Last one. This is the last slides for the challenges. Cheating attacks. So you could have people remember for collaborative filtering your method based on ratings, right? So in a rating system, you might have someone, okay, so here, in systems where anyone can provide ratings, you might have someone that would attack the system to benefit from the attacks. For example, people give positive ratings for their own materials. People give negative recommendations for competitors. Your CF systems wants to discourage this method. So some approaches, item-based methods are less affected than user-based because you are not really finding similar users. You are finding similar items for a specific user. Hybrid system will be able to provide some partial solution, but this is still a difficult problem. This is also now when you are on Amazon, you will be able to see some reviews are from confirmed purchase, right? So this gives you more confidence. But very often on eBay, you will see when you purchase some items, some small items, it's so cheap and it's shipped from somewhere else internationally. Very often the sellers is going to sell you very cheap items. They can take a loss, but with the return is that you will be able to rate their product and in turn rate their store so they can have high ratings. So this is still research work. All right, pros and cons, summary. CF-based methods work for any kinds of items. You do not need to generate characteristics of an item to be able to use CF-based approaches. You would have co-star problem. If you don't have enough users in the system, then you will not be able to find a match for recommendation. Sparsity, the user rating matrix is sparse, hard to find users that have rated the same items. So you do not have co-rated items or co-rated users, you will not be able to use both user or item-based CF approaches. First rater problem, you cannot recommend an item that has not been previously rated, right? You don't have any record for an item. Popularity bias, you cannot recommend items to someone with unique taste because you'll always use other people's opinion to help you to make the recommendation. Tends to recommend popular items as well, and this is usually very bad. All right, so that's everything about collaborative filtering, including user-based approach, item-based approach, and model-based approach. And the last one I'm going to talk about is hybrid method. But since today we are going to have a quiz, and our quiz today is pretty long, I am going to start the quiz right now. So let me upload the quiz. You will like the quiz today. Okay, for the quiz today, you can use a calculator. So make sure you have a calculator with you. And it's due at 8 p.m. And you should be able to find your quiz on Blackboard. You need a calculator. Well, you don't need a calculator. You can use a calculator. You don't have to. All right, so your quiz is on Blackboard. You can start now. Submission time, 8 p.m. today. Again, 8 p.m. today. If you're watching the lecture and you are late for your quiz because you thought the quiz will start at 7:20, please do not send me an email. We just start now. You don't have 10 minutes extra. All right, let's start the quiz. Turn on your camera so that I can see you. Your TA will be here at 7:20 to look at your camera feed. But if you have any questions about your quiz, here, this is the time to ask. Still have a couple people who did not turn on the camera. Please turn on your camera.
All right, question one, there's a question. So should question number one be user one, item two? No, it's user three, item two. There's a question mark because I took a screenshot from the slides.
Time is up, so you can upload your answers to Blackboard. And my office hours will start in 10 minutes. So if you have any questions about homework 3, you can come to my office hours.
Hello, TA. I remember that the professor said we ended in 8 o'clock.
Okay, sorry.
Yeah.
He didn't tell me about it. Okay. So
Okay.
Okay, time's up. So you can upload your answers.